Okay, let's look at some of these short answer questions. So first set of questions is all about water. Okay, water has a very high heat capacity. A bomb calorimeter filled with 1.00 times 10 to the fourth grams of water has a temperature increase from 25 degrees Celsius to 45 degrees Celsius when a Twinkie is burned. Calculate the heat energy Q released in calories and capital C calories. Given the specific heat of water, CW, is 1.000 calorie per gram degree Celsius. I'll start in as and then give that there. We need our answer with three significant figures, three sig figs. Okay, so let's kind of outline the data we need from this. Okay, so we've got our grams of water. We've got our specific heat capacity right there. Okay, we've got our temperature increase. Okay, we want to figure out the heat energy Q. Okay, so our calculation, our equation for this looks something like this. Q equals M for the mass of the substance, C for the specific heat capacity of the substance, delta T for the change in temperature. That didn't come out very well. Temp change. Okay, which is equal to the final temperature minus the initial temperature. Okay, that way, if the change is positive, like if our temperature increases, then we get a positive number, a positive change, and if our new temperature is lower, then we end up with a negative number, and so we have a negative change. Okay, so in this case, our temperature is going up, so we're going to get a positive temperature change. Our mass has to be positive, our specific heat capacity has to be positive, so our Q is going to be positive also. That means we are taking heat into the water, we're absorbing energy. Okay, Q means it's absorbing if we have a positive Q value. Okay, so we burn this Twinkie, it releases a bunch of heat, and we essentially get that heat absorbed by a sample of water. In this case, 1 times 10 to the fourth grams. So let's throw into this stuff what we have to calculate. Okay, so Q is going to be equal to, okay, our mass is 1 times 10 to the fourth, which would be, let's see, be like 10,000 grams, I think. 1.00 times 10 to the fourth grams times our specific heat capacity. Now, in our practice, we might have used the specific heat capacity in joules per gram degree Celsius, and it would look something like this, where C is 4.184 joules per gram degrees Celsius. Okay. The specific heat capacity we have over here is the same. It's just that 1 calorie is the same as 4.184 joules of energy, which, there you go. So the calorie looks like a kind of more easier to work with sort of thing for the math. It's just a matter of, what am I trying to say? Which way I preference, I guess. So in this case, they want it in calories, so we're going to do it in calories. Okay, so our specific heat capacity is 1.0 calories. And actually, since they want this with 3 sig figs, we should probably have at least 3 significant figures in this. Calories per gram degree Celsius. Okay, so both of those are kind of in the per part of the unit, which is why they have a -1 exponent there. And then our change in temperature is 45 degrees Celsius minus 25 degrees Celsius. Okay, so let's see, this should be 20 degrees. Oops. 20 degrees C. And then times 1 is just going to be 20. So let me actually just sync this up a little bit. So this will be 20.0. Okay, because we're taking 45 minus 25, that's 20 times 1 Okay, now our degrees Celsius unit is going to be canceling out with this per degree Celsius. So we're just left with calories per gram. Okay, which is then going to be multiplied by 1 times 10 to the fourth. Whoops, it's 111 times 10 to the fourth grams. Okay, so this was 20 degrees Celsius. So our grams units are going to cancel out. We're going to be left with just the units of calories. So it's going to be 20 times this 1 times 10 to the fourth, which should leave us with, let's see, that would be, well, 20 times 10 to the fourth. So if you wanted to fix that scientific notation, it would be something like 2.00 times 10 to the fifth. And then our unit is calories. And we want to make sure that we have 3 significant figures, which I do here, 2 and a 0 and a 0. So that's cool. So our heat energy absorbed by the water from the heat of the Twinkie burning is 2.00 times 10 to the fifth calories. But capital C calories is what we usually see on food. This is actually kilocalories. Okay, so if I wanted to convert this to kilocalories, I would just have to move the decimal place a little bit. I'd move it 3 spots to the left to change it from regular calories to kilocalories. So if this regular lowercase c calories is 2.0000, because it's, oh, I did that wrong right there. So past the 0, past the 0, past the 0, yeah, it should be like 20,000. Okay, calories. That should be equal to, moving our decimal place to the left, 3 times. I did something wrong. If you eat a Twinkie that's 20 calories, then you lucked out. I think I have a decimal place wrong somewhere. Yeah, because I didn't move enough spots. Well, let me back that up. As you can tell, I'm on the top of my game right now. If I'm moving this 5 spots to the left, I should have 5 zeros. So we have 200,000 lowercase calories, which then we move the decimal place 1, 2, 3 spots to the left, and we get 200 capital C calories, which is also known as kilocalories, which is much better. Seems to make a lot more sense. Again, if you have a Twinkie that you're eating that's only 20 calories, then sign me up, but usually not that healthy. Okay. Complete the following calculations and conversions. Show all work in units. Okay, to the correct number of significant figures, what is the volume of water in the graduated cylinder? Okay, well, if each one of these lines is 1, 2, 3, 4, 5, each one of these is 1. This would be 6, 7. So we're going up to 7. Okay, we're going to assume this is milliliters. Oh, yeah, milliliters. This is in milliliters. So this is 7 milliliters. But where do we count the Sig Figs? So usually we do Sig Figs for measurements from glassware and materials and stuff, either based on what the glassware is how it's made, or we look at kind of where the demarcations are, kind of like where we graduated at, where our lines are. So we basically look for kind of the first digit of uncertainty and stop there. So for instance, on this graduated cylinder, I know exactly where 5 is. I know exactly where 6 is. I know exactly where 7 is. I would know exactly where 8 is if we got up that high. I don't know exactly what happens in the middle here, like in this section between these two lines. So that's kind of my first digit of uncertainty. So I kind of go 1 decimal point past what I would normally be able to just normally measure using the lines that were kind of given. 7.0. So I can go out to this uncertain digit where I can say it looks like it's right on 7. So I can say 7.0. And if it was a little above, maybe 7.1 or 7.2, but I don't know exactly for sure. I know we've hit at least 7 for sure. This one, so this one's yes, this one's maybe. Okay, we stop it there. So 7.0 milliliters should be our answer for this one. Okay, how many moles of water are in 240 grams of water? We need 3 sig figs. Okay, let's do this. This is just a little bit of conversion. 240 grams, and we're going to need some stoichiometry. Okay, well, I guess not stoichiometry. I think it's technically for reactions, but usually we think of this and people are like, oh, this is stoichiometry, but it's really just unit conversion, just fancier unit conversion. So 240 grams of water is what we are converting here. I want this in moles, so let's multiply by a fraction bar. I'm getting rid of grams, so I'm putting grams on bottom. I'm trying to get to moles, so moles is on top. So I need a conversion factor that takes me between grams of water and moles of water. So how many grams of water are in a mole of water, or how many moles of water are in a gram of water? Well, probably the first one, probably the prior. So how many grams of water in a mole of water? Well, we call that relationship the molar mass. Okay. And the average atomic mass that we see on the periodic table, aside from just being a measurement in atomic mass units, AMU, also is molar mass. It's how many grams of that, that element will be how many grams of that element there will be in 1 mole of that element. So if I'm dealing with water, which is H2O, okay, then I just have to look up the molar mass of 2 H's and 1 O and add them up. Each H is about 1.01 grams per mole. Each O is about 16 grams per mole. So in total, this should be 18.02 grams for every 1 mole. We love to be 1 with moles. Okay, so 1 for the moles, 18.02 grams down on the bottom. So if we just multiply and divide this out, we should get our answer. So I'm going to take 240 point, and then divided by 18.02, and I get 13.32. 13.32. Okay, grams cancel out, and I'm left with moles. Okay, but there's an issue here because, again, I need it at just 3 sig figs. So right now, I've got a 1 and a 3 and a 3 and a 2, and these are all significant. So I should chop off this last one and round it. This would round down to just 3, so that's gone. So 13.3 moles is my answer for this one. Okay. Let's use this in the next problem, because now we want to figure out how many molecules of water are in 240 grams. Well, I mean, we found out how many moles are in water, and we have a relationship between moles and particles. Okay, so let's write this up. So I've got 13.3 moles of water. All right, and I'm going to multiply by a fraction bar to try and get rid of this stuff. I want to get rid of moles on bottom this time, and I want to get molecules on top. Now, whether we are talking about molecules or single atoms, or a big or small compound, doesn't really matter. A particle is a particle. We're looking for stuff stuck together. So either single atoms or stuff bonded counts as a particle, again, big or small. We have a relationship between moles and particles of all shapes and sizes. A mole is 6.02 times 10 to the 23rd of anything. We call this Avogadro's number, because he's the guy that kind of figured it out. And again, we like to be 1 with moles. So in 1 mole, we have 6.02 times 10 to the 23rd, right there. So all I have to do is multiply this out. I end up canceling my moles units. I'll convert this to molecules. 13.3 times 6.02. So this is 80.066 times 10 to the 23rd molecules of water. All right, and if you wanted to fix the scientific notation, bump this over one more, and this is also the same as 8.0066 times 10 to the 24th. Okay, now still only can have 3 sig figs, so let's round this. I've got this sig fig and this sig fig and this sig fig. So these guys I'm going to have to cut out. I'm going to round back to this decimal right here. So I'm going to round up to 8.01. I'm going to have my times 10 to the 24th there. Molecules. Oh, that was bad. You get the idea. Molecules of H2O. Okay, last step. How many hydrogen atoms total are in 240 grams of water? So we're still using the same quantity of water. Just taking this one step further. Okay, we want to figure out how many hydrogen atoms there are. Okay, well, we had molar mass as a relationship between moles and grams. We have Avogadro's number, which is a relationship between particles and moles. Avogadro's number, big nasty number. Okay, we don't have any strict rule or relationship between a certain number of atoms and a certain number of molecules. It just depends on what substance we're dealing with. So if I have a molecule of H2O, okay, that has 2 atoms of hydrogen and 1 atom of oxygen. That means if I have a mole of H2O, I've got 2 moles of H and 1 mole of O contained in that compound. So we now have a relationship for this based on that, the formula of the compound. Okay, so 8.01 times 10 to the 24th molecules H2O. I'm going to convert this, where this time I am getting rid of molecules of H2O. Instead, I want to know atoms of H, atoms of hydrogen. Well, molecules of H2O is going to cancel. Okay, and in 1 molecule of H2O, I have 2 atoms of hydrogen. So all I have to do is really multiply this by 2. This should come out to be 16.02 times 10 to the 24th atoms of H, or again, you could fix the scientific notation and make that 1.602 times 10 to the 25th atoms of H, atoms of hydrogen. All right, so these problems tend to be a little bit tougher because we're used to looking for the molar mass and the Avogadro's number and things like that. Okay, but stay calm, watch your units, and it will lead you through the problem. Let's keep going. On the following table for water, dot structure. All right, water looks something like this. O in the middle, H on the side, H on the side. It's got 2 lone pairs of electrons. Okay, so we could probably clean that up a little bit. I'm going to put these guys kind of, whoops, on the opposite sides over here so they have kind of their own room, okay, which is going to affect their shape. Now, if you're seeing me draw this and you're like, well, I don't think I would have gotten that straight off the bat. Am I supposed to memorize that? No, I'm just used to drawing it a lot. So you might draw it first like this, H, O, H, where you have two lone pairs on the middle there. And it looks like a linear molecule. But these lone pairs have to push things out of the way. So if we kept these 90 degrees apart from each other, that would be a little troublesome because we can actually get them farther from each other than that if we use the third dimension, if we start pushing things in and out of the page or the screen. So instead of leaving this kind of flat and linear, if I make these kind of crooked and I put kind of, let's see, one of these sort of out of the page, okay, or maybe in both of them kind of out of the page coming at you, they're kind of bending towards you, that gives us what we call a bent molecular shape. Okay, that bent molecular shape comes from where our lone pairs of electrons have to have their spots too. So our electron geometry takes into account these 4 electron domains, 2 bonded atoms, 2 lone pairs of electrons. We call that tetrahedral for those 4 electron domains. If all 4 of those domains were bonded atoms, we would call the shape tetrahedral also, but we don't. All we see in terms of where the atoms wind up is this bent shape, which is how we get this picture of water that we know so well by now, hopefully. Okay, the bond angle that we wind up with is not quite 120 degrees. It's more like 109.5. Okay, where it's sort of like a tripod. Like you have like one there. This one's coming out at you. There's one going behind. There's one going up. So it's a little bit bigger than 90 degrees. But it's a little bit less than 120. Okay, but I'm going to erase this so that doesn't get confusing. It's not the best drawing. Okay. Now, the electronegativity difference between oxygen and hydrogen is pretty significant. So these are polar bonds. But when we care about whether the molecule is polar or nonpolar, we look more for how the electron cloud is symmetrical or asymmetrical. In this case, because we have lone pairs of electrons, we end up with our electron cloud being kind of more lopsided. We have the electron density kind of pulled up towards the oxygen. The electron cloud is kind of pulled more towards the more electronegative oxygen atom. So this ends up being more partially negative up here and more partially positive down by the hydrogen atoms. Okay, so overall we have a net dipole going up this way. Okay, so this is going to be a polar molecule. Okay, this redraw shape and show net dipole would be like if we started with this kind of linear shape and we needed to redraw it to show that it was actually bent. And show our net molecular dipole going up like that. I'll give me my lone pairs. Like that. Okay. Now, since this has a dipole, it's a polar molecule, when we put more than one polar molecule together, we get dipole-dipole intermolecular forces. Okay. Now, more specifically, if that dipole-dipole happens from atoms like oxygen or nitrogen or fluorine bonded to hydrogen that are very electronegative, then that makes a special kind of hydrogen bonding, or a special kind of dipole-dipole bond, intermolecular force called hydrogen bonding. Okay. Now, technically, also everything runs into London dispersion forces. Everything has a little bit of push and pull from their electron clouds being jerked around and accidentally showed up more this way, and then it attracted something or bullied another thing's electron cloud and induced a dipole that way. So there's always going to be a little bit of London dispersion forces with every atom or molecule or whatever that you bring close to each other. But the dominant stuff that shows up here is a special kind of dipole-dipole called hydrogen bonding. Okay. If we were to draw that out, let's put, well, actually I need this a little farther down, I think. If I put a water molecule here, actually let me do this in a different color. So there's my water molecule. Again, down by our hydrogen atoms, we have partial positive charges. And by our oxygen atom, we have partial negative charges. I'm going to leave off my valence electrons on the oxygen just so I have a little bit more room. Okay. So if we wanted to show intermolecular forces to 4 other water molecules, well, this partially positive hydrogen atom can go attract to another partially negative atom over somewhere else. So let's do that. So let's give some dots here to show our intermolecular force. So this is our hydrogen bonding going on here. Let me do it in orange so it kind of matches. Okay. So this would need to match up to a partially negative atom, which would be oxygen, if we're looking at something partially negative on another water molecule. So let me put in my other hydrogen atoms, just kind of sit them on there somewhere. Okay, and again, this is where we're lining up with partially positive with a partially negative, where these guys are partially positive over here. Okay. We can do the same thing to this hydrogen over here. Something like that. Put another hydrogen over there, put another hydrogen over there somewhere. Doesn't really matter how it's arranged as long as our partial positive of one molecule is lining up with the partial negative of another. Okay. It'd be best to try and keep the partial positives of one thing away from the partial positives of the other. So this is probably a little bit more favorable than this. So if I wanted to draw this a little bit better, I would probably put this over here. Something like that. Okay, now this partially negative end of the water molecule can also go and attract to other stuff. So let's do 2 more of these. So partially negative end of this water molecule is going to attract to a partially positive end of a different molecule, like the hydrogen atoms over here. Okay, and I can do kind of the same thing over here. Okay, where our hydrogens are partially positive. Okay, and then if I wanted to, I could put all the rest of the partial positives, but I think you get the idea. All right, let's keep going. Number 47, atomic structure and nuclear decay problems. Okay, so we're going to complete this table. All right, this number up in the top left of an atomic symbol is called the mass number. And the mass number is equal to the number of, actually, it's right there, let me right over here. This mass number, I'm going to call it M, is equal to the number of protons plus the number of neutrons in an atom. Now, the number of protons is pretty easy, because as long as we know the element, we can go look it up on the periodic table. And the big number in the top left or the top middle of the periodic table for that element is the atomic number, and it's the number of protons. Okay, so if I go look up Neptunium, that should tell me how many protons it has. A lot of periodic table here. So let's see, NP for Neptunium, there it is. It has 93 protons because it's atomic number 93, which, hey, matches right there. So that's good, we're on the right track. Okay, now as long as your atom is neutral, the number of electrons should match that. So our total number of electrons, not just valence electrons, our total number of electrons should match our number of protons, okay? If our atom is neutral, okay, in other words, there's no charge in the top right up here, okay? That means that all that positive charge from the protons has to be canceled out by some negative charge of the electrons, the same amount, okay? So by saying that we have 93 electrons here to match the 93 protons shows that it's electrically neutral. All our positive charge is canceled with negative charge. Okay, therefore our charge in this case is 0. Nada, nothing. Not positive, not negative overall on this atom. Okay, so the last thing we need to figure out is the number of neutrons. Again, we can get that from the mass number. If our mass number is 239 in this case, based on what our symbol tells us, okay, well, if we take our number of protons plus neutrons, which is our mass number, and subtract out the number of protons, what's left is the number of neutrons. So 239 minus 93 leaves us with how many neutrons we have in this atom, which is 146 in this isotope of neptunium. Okay, in the next example, we don't know what the element is right off the bat, but we can figure it out. Okay, since we are given the number of protons. The number of protons is the atomic number. So if I have 17 protons, this is atomic number 17, and if I go look that up on the periodic table, that is chlorine. Okay, now if you like writing the symbol kind of full out, we sometimes put the atomic number down in the bottom left, but chemistry teachers and professors and whatever love to leave it out so that way you have to go and track it down on the periodic table to figure it out. I think this is more helpful, but maybe that's just me. Okay, our mass number is given to be 37, which is that number in the top left of our atomic symbol. Okay, let's see, our number of electrons should match our number of protons if this is neutral. Ooh, but this isn't. This has a charge of -1. What does that mean? That means that we have an extra negatively charged electron, one more than we usually would. So if we usually had 17 electrons to match our 17 protons, but then we have one extra to give us a -1 charge, that means we actually have a total of 18 electrons in this atom, this version of chlorine. And we could show that by giving it a charge up here on our symbol, do a little negative sign. Okay, we could write 1 negative, but we don't really need to. It's kind of implied. All right, the number of neutrons, and last thing. That again can just be figured out from the mass number and the number of protons. If I take the number of protons plus neutrons and subtract out the protons, what's left is the number of neutrons, and that should be 20 in this case. All right, our last example is an isotope of calcium. Okay, our number of protons is given, which is nice. Again, that should be the same as our atomic number. So calcium is number 20 on the periodic table. Okay, our mass number in this case is also given. It's this 40 in the top left here. Okay, and just to check, 40 minus 20 should be our way to get the neutrons. So 40 minus 20 is left with 20, which is how we get that 20 right there. Okay, so two different isotopes, but they both end up with 20 neutrons. It's kind of funny. Okay, our number of electrons should kind of follow the number of protons, but we also have to take into account the charge. This has a charge of +2, 2 plus. Or you can say +2, I guess. There is -1 here, so I guess I'll follow their trend of +2. But if you write 2 positive, that is also fine. Okay, so if we usually have 20 electrons to match our 20 protons, we have a +2 charge. That means we've lost 2 negatively charged electrons, and therefore the atom is left more positive. So 20 minus those 2 electrons leaves us with 18 electrons. All right, so the only difference between these two isotopes, they have the same number of total electrons, they have the same number of neutrons, the only difference is the number of protons, and that is what determines the element. Okay, let's keep moving. All right, so our element iridium has an atomic weight of 192.22 AMU and only 2 stable isotopes. One isotope has an abundance of 37.3% and an isotopic mass of 190.96. Based on this data, what is the mass of the other isotope in atomic mass units AMU? Answer to 5 Sig Figs. Ooh, okay. Well, let's math this out. All right. Our average atomic mass of an element, I'm going to say average AM, is a weighted average that depends upon how many isotopes you have, and how abundant those isotopes are, and what their masses are. Okay, and it usually follows this general trend. We have the mass of one isotope times the abundance, the percent abundance as a decimal, okay, of that isotope, plus the mass of the second isotope times its percent abundance as a decimal, plus the mass of the third isotope, and then this just keeps going and going and going for as long as you need to, for as many isotopes as you have. Okay, in this case, we only have two isotopes, so we're not going past basically this point right here. The bouncer escaping from me. Come on, there we go. Okay. Now, the average atomic mass is what's on the periodic table. So since I know this is iridium that we're looking at, if I go look up iridium on the periodic table, I should be able to get its average atomic mass. So iridium, oh, and it also says it up here, atomic weight, okay, is 192.22 AMU. That atomic weight is the average atomic mass. Same thing, different word. So 192.22 AMU. That is that special weighted average that tells us basically how heavy the element is overall based on the different isotopes that we can find in there, how abundant they are, and what the mass of each one is. Okay, so let's fill in some information that we know. Get this out of the way. Okay, so we are, I don't know why that keeps doing that. Okay, well, I guess I'll just see you later. Bye. Okay, so the mass we're given for this first isotope is 190.96 AMU. Okay, its percent abundance is 37.3%. As a decimal, two spots to the left, that is 0.373. Okay, so by multiplying these two, I basically get the contribution of this isotope to the atomic weight, or the average atomic mass. Okay, we'll get back to that in a second. This should be added to the mass and the percent abundance of the other isotope multiplied together. But I don't have either of those. I'm looking for the mass of the other isotope. Okay, I don't have the percent of the other one, but I do know there's only two isotopes. So if I take 100 minus that percentage, 100 minus, oh, sorry. I should be a little bit more careful about this. Hold on. Let me do it outside of the problem here for a second. 100 minus 37.3, that'll give me my percentage, which I can then change into a decimal to put here. So 100 minus 37.3 is 62.7. So this other isotope is 62.7% abundant. They're 62.7% of the time. So 0.627 is going to be that number I plug in there. Now I just have to solve out for m, and it's just algebra from this point. Okay, so the hardest part is kind of remembering how to set this up, where to put the numbers in the right places, and then it's just math from there. So if I take 192.22 divided by 190.96 divided by 0.373. Oh wait, hold on. I'm getting ahead of myself. Let's multiply these two. Let's crunch these together. 190.96, 190.96 times 0.373. That is 71.228. That should be equal to 192.22 AMU plus this m times our 0.627 we haven't dealt with yet. I can subtract this from both sides, 71.228 minus on both sides. So 192.22 minus 71.228 gives me 120.992 equals M. Oh, my pen is really lagging. It keeps dragging. M times this 0.627. So the last thing I need to do is divide off this 0.627, and I should get my mass. So 120.992 divided by 0.627 is M equals 192.969. Okay, AMU. All right, and since I want this to be to 5 sig figs, I've got 1, 2, 3, 4, 5, 6 right now, just from how I kind of got it from my calculator. Let's round this to 5 by rounding it up. Round this up to 97. 192.97 AMU is what I'm looking for my mass of this other isotope. So probably our isotope is iridium 193, because that's pretty close to that mass, that atomic mass. Okay, what is the mass defect in grams per mole of neptunium-239? Okay, so we're given molar mass of neptunium-239. We're given the mass of a proton. We're given the mass of a neutron. We're given the mass of an electron. Ooh, okay, well, let's try and put all this stuff together. So neptunium-239 is just like that isotope we had up here. This guy right here, which has 93 protons and 146 neutrons. Okay, so 93 protons, 146 neutrons. Okay, and I think we also had 93 electrons to match because this was a neutral atom. Okay, so let's see. Mass of our proton is 1.00730. 1.00730 grams per mole. All right. Mass of our neutron is 1.00870 grams per mole. And then our mass of our electron is 0.00055 grams per mole. Oh, hold on. 5. Oh, there's another 0 in there. I missed a 0. Try that again. 0.00055 grams per mole. Okay, so let's add all this up, or rather multiply it first and then add it. 93 times 1.00730 gives me 93.6789. 146 times 1.00870 gives me 147.2702. Again, this is grams per mole. This is grams per mole. And then 93 times 0.00055 grams per mole. Let's see. It's going to be 0.05115. My pen just gave up on me again, which is great. Maybe we'll fix it recently by just unscrewing it and screwing it back together, and then for some reason it starts working. Hey, there we go. Okay, so 0.05115 grams per mole is what I need. So let's add all that up. So 0.05115 plus 147.2702 plus 93.6789 gives us a mass of 241.00025 grams per mole. Okay, so this is what the mass of this atom or this isotope or mole is, or the mass in grams per mole. This should be for neptunium-239, but instead it's this 239.052939. So this is the actual mass. Okay. So that means that there is a mass defect based on how those things kind of attract each other and how the kind of physics works out of how they bind to each other. So our mass defect should basically be the difference between those two masses. Now I'm hurriedly kind of going through the book because I have a feeling that it matters which one you do first and which one you do second when you subtract them. And I can't remember off the top of my head. So let me see. I think it can just come out to be a positive number. Okay, what we do what should be minus what it should actually be. Okay, so we're going to take this 241, which I guess that makes sense. Yeah, it should be positive. 241.00025 grams per mole, what it should actually be, minus what it actually is, 239.05239 grams per mole. I'm just going to ditto mark that. And I can subtract this out, 241.00025 minus 239.0522939. I get 1.947311. 0.947311. Okay, now, if we're doing this to 5 sig figs, this isn't asked very well because I don't, when you add and subtract, usually your sig figs are all about what comes after the decimal place, but I don't know if that's what they want or if they want total sig figs. So if we did total sig figs, it would be 1.9473, and we chop the rest of this off. Keep this as grams per mole. But our lowest number of decimal places is 5 sig figs after the decimal place, like these guys here or these guys here. So if we were to do it like that, usually for addition and subtraction, we're looking at how many sig figs are after the decimal place. So it'd be something like that. But either way, it's going to be about 1.95-ish grams per mole as our mass defect. Okay, this neptunium-239 undergoes beta decay. This, I believe, is written upside down. This should be 0, -1 E for our beta particle, our high-speed electron that's kicked out. So when neptunium and P 239, actually, let me do this in purple, 239 with 93 protons, okay, goes through beta decay, a beta particle, this guy, is kicked out. So if you don't remember what beta decay actually does, that's okay. We can probably figure it out, okay? Because we're going to let loose one of these beta particles that has a mass number of 0, an atomic number of -1. Now, the law of conservation of mass tells us that we can't really lose any matter, it can only be changed. So our mass number has to be equal across the arrow, and our atomic number has to be equal across the arrow for the sum of the reactants versus the sum of the products. So my mass number, 239 on the left, should be equal to 239 on the right, and right now it's just 0. So I need something else with a mass number of 239 over here. On the left side, my atomic number is 93. On the right side, it is -1. So 93 has to be equal to something -1. So that is going to be 94. Okay, this can help me figure out what this other piece is going to be, okay, in this nuclear equation. So all I have to do is figure out what has an atomic number of 94. The mass number doesn't really tell me anything other than how heavy this specific isotope is, okay? But the number of protons always tells me what element I'm dealing with. In this case, we're talking about plutonium. Atomic number 94 is plutonium, Pu. Okay? So what happens in a beta decay is we have a neutron change into a proton and electron, and then some other stuff I don't need to worry about. Okay? The proton sticks around in the nucleus, which is why our atomic number goes up by 1 from 93 to 94. And the electron is ejected, flies out of the nucleus, goes soaring away, which is why we have this beta particle kind of separate here. All right, half-life problem. Neptunium-239 has a half-life of 2.35 days. How many grams of a 1 gram sample of this isotope will remain after 9.40 days? Now, there are a couple ways to go about this, but this is how I think I would see this. Every time we go through a half-life, we are dividing our mass of our original radioactive material by 2, okay? And that is 1 half-life. That is the length of 1 half-life. Okay, which in this case is 2.35 days. Okay, overall, from start to finish, this is supposed to take 9.40 days. So how do I figure out how many times this has a half-life, and therefore how many times this gets cut in half, and therefore how many grams of radioactive stuff are left? Well, if the whole thing is 9.40 days and each half-life takes 2.35 days, well, if I take 9.40 divided by 2.35, what's left is how many half-lives can fit into this. Since this is how much time it takes per 1 half-life, okay, how many times can I put this in here? So 9.40 divided by 2.35, 9.40 divided by 2.35 is 4. So I can fit 4 half-lives in here. So let's see if I can split this up correctly. 1, 2, 3, 4. That's kind of uneven, but that's close enough. Okay, so each one of these is going to be 2.35 days. There, right there, there, and right there. And every time I go through another 2.35 days, I lose half of that radioactive material. So I'm dividing by 2, I'm dividing by 2, I'm dividing by 2, and I'm dividing by 2 for each half-life that we go through. So this is our first half-life. This is our second half-life. This is our third half-life. This is our fourth half-life. All right. So if I started with 1 gram, that gets chopped down to 0.5 grams, which gets chopped down to 0.25 grams, which gets chopped down to 0.125 grams, which gets chopped down to 0.0625 grams. But this isn't the only way you can get to this answer. You can always draw pictures. I am a big fan of drawing pictures for these. Okay, and that should be the end of the short answer. So hopefully this has been helpful in kind of reviewing how to do problems just like these. So I'm just scrolling all the way back to the top, so there we go.